Alright, if you are watching this video, I'm going to assume you know who I am and what we're doing, so I'm just going to jump right into this. So the trick to any of these problems is knowing the right equation to use. So for these first couple, what we're going to need are the kinematic equations, which were the ones that looked like this. We had VI, or VF, equals VI plus AT. VF squared equals VI squared plus 2AD. D equals VIT plus 1/2 AT squared, and D equals 1/2 VI plus VF times T. Those can be found on the county formula sheet. So here we're told a truck accelerates to a velocity of 38 meters per second over 755 meters of road. That means since we're accelerating to 38, oh, and it says it's initially at rest. Okay, so VI is 0 since it's initially at rest. VF is 38. And D is 755. So what is its acceleration? And then how long will it take? So for acceleration, we look for the equation that has VI, VF, D, and A in it. That's going to be this one. VF squared equals VI squared plus 2AD. So that's 38 squared equals 0 squared plus 2 times A times 755. 38 squared is 1,444. 2 times 755 is 1,510 times A. 1,444 divided by 1,510 gives us an acceleration of 0.96 meters per second squared. Now there are a variety of ways we could solve for the time in part 2. We could use a lot of the equations. I usually try to solve it such that I'm not using my answer from part A, so I am going to use this last equation over here since it doesn't use acceleration. D equals 1/2 VI plus VF times T. So that's 1/2 times 0 plus 38 times T equals 755. So 19T equals 755. 755 divided by 19. T equals 39.7 seconds. Alright, for number 2, we'll be using the same equations, the kinematic equation. So it says a car accelerates from a stop sign at a rate of 3 meters per second for 8 seconds. How fast is it going? So since it's accelerating from rest, that means VI is 0 because it was at a stop sign. A is 3 meters per second squared, and T is 8 seconds. What we're looking for is V final. So we can just use the most basic of the kinematic equations. VF equals VI plus AT. 0 plus 3 times 8. And VF is 24 meters per second. That is perhaps the easiest problem on the entire study guide. All right, number 3 is a little bit different. We are not using the kinematic equations here. It says you have a boat heading north that crosses a wide river with a velocity of 10 meters per second relative to the water. The river has a uniform velocity 5 meters per second due east. So this is a vector combination problem. So we're going to draw a beautiful triangle. We have 10 meters per second going north and 5 meters per second going east. And we want to determine the boat's velocity with respect to the shore. So that's going to be the hypotenuse of this triangle here. So our A will be 10, our B will be 5. I always set B as our smaller number. So C is going to equal the square root of A squared plus B squared, which is just the Pythagorean theorem. So C equals the square root of 10 squared plus 5 squared. C equals the square root of 125, which means that C comes out to be 11.18 meters per second. But we are not done. That only gives us the magnitude. It does not give us the direction. To get the direction, we need the angle. You're going to use the inverse tangent to find that. The angle is equal to the inverse tangent of B over A. So the inverse tangent of 5 over 10. You'll know if you've put the right one on top, because otherwise you will get a angle that's greater than 45, which we don't want. I did not. I got 26.5 degrees. If you get a number that's greater than 45, then you've done this wrong. If you get a number that's negative or less than 1, it means your calculator's in radians and you should fix that. The last thing we need is our cardinal direction, which you always do short of long, which in this case is east of north. So our final answer is 11.18 meters per second, 26.5 degrees east of north. Part B, how wide is the river if it takes the boat 30 seconds to cross it? That's relatively simple. We would just use V equals D over T. He's traveling at 11.18 meters per second. It takes him 30 seconds. So 11.18 times 30 gives us 335.4 meters. This next one, the difference between distance and displacement. So distance is a scalar. It does not have direction, so it's just how much you've traveled total. Displacement is a vector. It does have direction, and it's how far you have traveled from your starting point. I'll go back and write those in later when I'm not recording. Number 5 is a projectile motion problem, which means it uses equations very similar to the ones we were just using, but that it is a little bit different. These are the ones that I strongly suggest you draw pictures for. So here we have a cliff. We have a ball thrown off the cliff. The cliff is 55 meters high and it's thrown with a speed of 0.75 meters per second. The height is going to be our dy. So dy equals 55. The speed it's originally thrown with is Vx. So Vx equals 0.75. And then they ask us for 3 things. How long is the ball in the air, which is time. Where will it land with respect to the base of the cliff? That's dx. And how fast is it moving when it hits the ground? That's going to be v yf, basically. So time is pretty simple. There is an equation on the formula sheet in the projectile section that says time is equal to the square root of 2 dy over g. So that's 2 times 55 divided by 9.8. Two times 55 is 110 divided by 9.8 is 11.22. The square root of that, well, hold on. So that was like 11.2. And the square root of that gives us 3.35 seconds. This is one of those where you cannot help but use the answer from part A to solve part B. Part B asks where will it land? Well, we already decided that was dx. There's a formula on the formula sheet for dx. It's vx times t. So we do 0.75 times 3.35 which gives us 2.51 meters. Lastly, we have to find the VYF, which we're going to use one of the kinematic equations. So we'll have VYF. Sorry, the lights turned out in my room, as they are known to do when I'm not moving around enough. But anyway, we'll use VYF equals VYI plus GT. VYI is 0, so it's 9.8 times our 3.35, and that'll give us VYF equals 9.8 times 3.35 equals 32.83 meters per second. All right, on to forces. The big thing to remember about forces is the free body diagram. It'll actually be a part of the credit, but it is also designed to help you. It really, truly is. So, here we have a 45 kilogram lab cart pushed down a hallway. A force of 312 newtons is applied to keep it moving at constant velocity. That constant velocity sentence is going to be super important. So, we're supposed to draw our free body diagram. There's going to be 4 forces. The first is gravity, which is always pulling downward. Then there's the normal force, which is preventing gravity from pulling the box through the floor. Then there is the applied force, which we know is 312 newtons. And lastly, there is the frictional force, which is pulling against the applied force. Now, the fact that it's at constant velocity is really important, because constant velocity means A equals 0, means no acceleration, and since F net equals ma, F net is going to be 0. So that means that all the forces in each direction have to cancel out. In this case, that means Fa and Ff have to cancel out, and Fw and Fn have to cancel out. So to find Ff, that's super easy. It has to be equal to F of A, but opposite, so it's going to be negative 312 newtons. Next, we have to find the coefficient of friction. Remember that that is mu. The formula for mu is F of F over Fn. We just found F of F. We need F of N. It's going to be equal to the weight. Weight is mg. We have a mass of 45. Gravity is 9.8. so that's going to be 441 newtons. So we can plug those two numbers in here. 312 divided by 441 gives us a mu of 0.71. Remember that mu should always be positive and less than 1, which this is. So
Alright, I apologize if there is background noise in this part of the video. They're watching a movie in the classroom next door and it's pretty loud. Hopefully my mic won't pick it up. Okay, so number 7 says find the parallel and perpendicular force components of a crate weighing 890 newtons that slides uniformly down an inclined plane that makes an angle with the ground of 26 degrees. So the first thing we should do is draw a beautiful picture here. So we're going to have our incline of 26 degrees. We have this crate. Forces acting on this crate. Gravity is pulling it downward. It's Fw. The normal force is pushing it upward. And because it's sliding uniformly, there must be something holding it up, which is going to be F of F. Luckily for us, we don't actually have to worry about F of N or F of F at all in this problem, because all it's looking for is the parallel and perpendicular force components. So we just need to break Fw down into its components. So what that looks like is you have F parallel, which is the component of weight that's parallel, and you have F perpendicular, which is the component of weight that's perpendicular. If you redraw the picture a little bit, makes it easier to see. We have Fw here, F parallel here, or no, F perpendicular there, sorry, and F parallel here. Basically, they make a triangle. You just have to use some basic trig here. F parallel is going to equal Fw sine theta. I think that's wrong. Let me think for a second. So the angle is basically here. We can redraw a parallel here. So that's opposite of hypotenuse. Okay, so that's right. Sorry. But that's the way you have to think about it. So this is opposite the angle, so that's sine. Then F perpendicular is adjacent to the angle. So that's cosine. They gave us the weight. Yay! 890. So we just have to plug things in. You'll need to make sure your calculator is in degrees. So F parallel is 890 times sine of 26. My calculator is actually in radians at the moment. So good. Okay. 890 times sine 26. So F parallel is 390.15 newtons. F perpendicular is 890 cosine 26. So F perpendicular is 799.9 newtons. Alright, number 3. There are 3 forces acting on a rock. 11 newtons west, 23 newtons north, and 32 newtons east. So my little crappy rendition of that is going to be 11 west, 23 north, and 32 east. We have to find the resultant and the equilibrium. We talked about this in class today, but resultant is the combination, and the equilibrium is the vector that added to the resultant cancels out. So to combine three vectors like this, two of them, combining vectors that are in the same direction or opposite directions is pretty easy. If they're in the same direction, you add, and if they're in opposite directions, you subtract. So here we have 11 west and 32 east. So that's going to be 32 minus 11, which will give us 21. I'm an embarrassment to need to use a calculator for that, but sometimes I doubt myself. Yeah, okay. So now we have 22 newtons east, and we still have the 23 newtons north. So we can basically redraw. It's now a triangle. That has sides of 23 and 21. To find the resultant, we need to find C, and we need to find that angle. Finding C is easy. It's Pythagorean theorem, so it's going to be the square root of a squared plus b squared. 23 is going to be a, and 21 is going to be b, because we want our smaller number to be b. So we're going to have C equals the square root of 10. C equals the square root of 10 squared plus 5 squared. C equals the square root of 125, which that comes out to 11.18 newtons. But that's only the magnitude. We still need the direction. To get this angle, we're going to use the inverse tangent. So tan negative 1 of b over a equals theta. So theta equals the inverse tangent of b is always our smaller number, so it's going to be the inverse tangent of 5 over 10. Inverse tangent, 5 over 10. And that comes out to 26.5 degrees. We know that's pretty reasonable because it should always be less than 45. If it's greater than 45, you have your A and B flipped. If it's a negative number or less than 1, it means that your calculator is in radians. So, and then the last thing we need is the cardinal direction, which is always short of long. Here, if you look at this triangle, east is short, north is long. So our answer for part A is 11.18 newtons. We'll round and say 27 degrees east of north. So B is the equilibrium. It makes the total 0. So we want exactly the same magnitude, 11.18 newtons, but this time it's 27 degrees west of south. So the difference between the resultant and the equilibrium is just you switch the directions. Then part C says when the equilibrium force is applied to the system, we say the system is at equilibrium. That means that the net force is 0. All right, number 9, the one that I actively avoided working before because it's kind of funny. So this is another one where a diagram is going to be really important. So a box is being pulled across the floor at constant velocity. That's probably going to be important. they're using a force of 45 newtons to pull the box, but they're doing so at an angle of 33 degrees above the horizontal. The box weighs 92 newtons, so we can go ahead and draw FW is 92. There's some other forces that we know have to be acting. There has to be a normal force, and for it to be going at constant velocity, something must be balancing this applied force, which is what this is. This is an applied force. So there must be a frictional force balancing the applied force. So, normally we could just set things across from each other equal to each other. The problem is that as it stands right now, f of a is not across from anything. It's at this funny angle. So we have to break it into components, much like we did up here, the one that was on an inclined plane. So if we redrew our forces, they would look like this. Fn, Ff, Fw. We're going to split this into two pieces, because you have Fa. But basically you have Fa in the x direction, and you have the component of Fa that's in the y direction. This is, again, 33 degrees. So again, like we did up here, we just have to solve for this Fax and Fay. Fax is adjacent, so that's... Okay, sorry about that. So Fax is adjacent, so it's going to be Fa cosine theta, and Fay is going to be Fa sine theta. So that's going to be 45 cosine 33 and 45 sine of 33. Plugging those into my calculator. This one is 24.5. 45. And this one is 37.7. So, once we have those, we can kind of set things equal to each other. The force of friction is going to be equal to Fay, because it's at constant velocity, so everything's canceling out. And the only thing that's directly across from F, the force of friction, is the x component of the applied force. So the force of friction is going to be negative 37.7 newtons. I'm not really sure what all this problem wanted us to solve for. If you were going to find the normal force here, it would actually be kind of strange, because Fw has to be balanced out by everything that's pulling upward. Usually that's just the normal force, but here it's not. Here Fw needs to be balanced by the normal force plus the y component of Fa. So Fay. So we would have like 45 equals Fn plus 24.5. So we would get that the normal force is 20.5 newtons. It didn't specifically ask for this. Again, guys, I would not choose this problem. This is a pretty complicated problem. We didn't work one like it. Choose something else. But that's what it looks like if you're really determined. Alright, last force problem. A ball weighs 35 newtons. At one point during its fall, it encounters an air resistance of 16 newtons. What is the mass of the ball? What is the net force acting on the ball at that moment? What is the acceleration of the ball if it was falling without air resistance? And what is the ball's acceleration including air resistance? So here's what we have. We have a ball that we're still going to draw as a square because we are physicists. It's being pulled down by gravity, and it is being held up by air resistance. So the first question, what is the mass of the ball? That's pretty simple. Weight is equal to mg, and they gave us weight, so we would just have to say 45 equals m times 9.8, and you get that the mass of the ball is 4.59 kilograms. What is the net force acting on the ball at that moment? So F net is the sum of the forces. In this case, the sum would be the weight pulling down minus air resistance pulling back up. We have to do minus air resistance since they're acting in opposite directions. That's super important. So we have 35 minus 16. So F net equals 19 newtons. Now, what is its acceleration if it was falling without air resistance? In the absence of air resistance, the acceleration of any falling object is g, 9.8 meters per second squared downward. Easy enough. That's just kind of a trick question. See if you're paying attention. Then it asks, what is the ball's acceleration, including this air resistance? So to find this, we have to use the fact that F net, in addition to equaling the sum of the forces, is also equal to mass times acceleration. So we have 19. We found the mass up there. So we have 19 equals 4.59 times the acceleration. 19 divided by 4.59. And I am getting that it's 4.13 or 4.14, I guess, meters per second squared downward. So it's still falling downward, but the air resistance is causing it to fall downward slower than it was before. This is about the halfway point, so this is where I'm going to break my video.